In this video, as a continuation from the last video, we are going to discuss what Maxwell termed as the displacement current versus what we already understand and what we term the conductive current. So this is the correction term in Maxwell's equation number 3, and that is that my pen is not working. There you go. This term right here, I sub d. And so what does Maxwell say this term is? I sub d, he said, was epsilon naught d phi e over dt. So that is, he's saying that it's related to the change in magnetic flux, right? So what does this mean, right? Where's this or not magnetic flux, electric flux, right? What is this saying? Where's the change in electric flux? Well, we can see in a capacitor in this setup that here there is no current, right? So there is no this traditional current, that would be 0, right? But there is there's this imaginary current, and I have to stress that this is not actually real. It's just a kind of a correction, right? It's like a crutch to solve something that isn't necessarily there. So there is an E field, right? It's going from here to here to here, and it is changing as charges build up, right? So it's strengthening over time. And thus the flux is changing. And so what Maxwell found is that there was indeed a magnetic field that is induced by this electric flux inside from these capacitors. And so let's try to derive this notation, because I believe that it's kind of glossed over. So first, I want you to attempt to come up with recall a formula for describing charges on a capacitor. So I'll give you a minute to think about that. And so hopefully you are thinking the same thing as I was, and that is that Q is equal to CV. So first, let me erase my work here, right? So Q is equal to CV, right? That is relating some voltage to the capacitance is equal to charge on a capacitor, right? But in this case, the charge is changing, right? And thus voltage is changing, but a capacitance is a defined value, right? So we can describe this as a small amount of charge at any given moment related to the capacitance, right? It's a defined value for a capacitor, right? And a small change in V. So we'll denote that by saying small v, right? Now, you might be thinking right now that how in the world is this related? But you will see very quickly that this is directly related to what I wrote previously, which I will write right here for clarity. So Q is equal to CV, right? And is there another way we can write capacitance, right? Is there a related formula? So I encourage you to try to think about that. And is there a related formula for voltage? Relating to electric fields, right, E, and some distance, right, and areas, right? I'm giving you hints here. So capacitance is related to the following formula we can remember from earlier parts of electricity and magnetism, epsilon naught A on D, right? And voltage just for a capacitor and strictly parallel capacitors, ED, right? So E for the electric field and D for the distance in between, right? And so if we put this together, we get Q is equal to epsilon naught AD, right? So that's the capacitance times voltage, so a tiny amount of voltage in D. And then we get this, we cross it out, and we get that is equal to epsilon naught EA. And so, interesting. So we have defined the amount of charge on this given random capacitor, right? And we get this term EA. What is that from? And besides, don't say the gaming company, it's the electric flux, right? The amount of E field through a given area, right? We can rewrite this as E epsilon naught phi sub E, right? Electric flux. And so if you don't remember that, I encourage you to go look back on some stuff on Gauss's law, right? You should know by this point what electric flux is. So thus we have this new relation, which I'll write here because I'll erase this to write some more. Q is equal to epsilon naught electric flux times electric flux. So let's erase this to make some space. So now we have to think there is this imaginary current that we're being told that is here, right? Because we know that a current will produce a magnetic field. So how do we get this current, right? Well, what's the definition of current, right? Current is the derivative, right? The time derivative of charge, right? So charges per time, or changes in amount of charge per time, right? And so, wow, look right here. We just derived a equation for describing charge on these capacitors, right? So conveniently, we can define the imaginary current there as the derivative of epsilon naught phi E, right? And epsilon naught is constant, and thus we get that ID, right? So this kind of imaginary current, and I keep stressing it, it's truly imaginary, it is not actually there, right? You can obviously tell there is no wire in between the capacitors, so it's not truly there. Is epsilon naught, right? We factored it out, d phi E dt. And look at that, we just derived it. And so in the following video, I will describe how we can actually use this to see the magnetic field within the confines of the capacitor, and so a given r distance away from this capacitor, and then outside of this capacitor, so like a further r distance away. So we'll discuss that in the following video.